greeted. Let's look at, oh, I didn't say what we're going to do. We're going to do, let's review, oh, two fancy letters, right? Review of quiz 9, and that is on 7.2 power series solution, but it's the easier part of it. We do the other one in the next quiz. And so these are the special type of power series that are easier to deal with. And where did I put my notes now? Ah, okay, here. So let's look at the first one here. I have the x squared plus 1 y double prime plus xy prime plus 2y equals 0. Okay, and let's look at the initial conditions that y of 0 is 10 and y prime of 0 is 40. Okay, now either one has to, I'll say it explicitly, or you have to deduce it from the initial conditions that what type of power series we want. Well, since these are the initial conditions, this means that the center has to be 0. So this means that the center x0 is 0, so we're looking for something of the form an x to the power n. Okay, and let's write down the derivatives, because we're going to have to plug this in. Okay, we plug this in, we get x squared plus 1 times summation n minus 1 an x to the power n minus 2 plus x times summation n x to the n minus 1 minus 2 times summation an x to the n equals 0. Because we plug it in and we're always looking homogeneous ones here. And the only thing we have to expand the first one. This gives me, let's do this one first, because that's the special one, right? Because this one doesn't have the right power yet. But the next one, because we are in this easy case, all the powers will now match up. Okay, we have this x squared together with that will give me x to the n, and the same here. So that being the case, I can already say, okay, I know that everything here will have an an x to the n. And so what will this be? Well, I now write down n times n minus 1 plus 1 minus 2. That is just taking all these terms together already. I'm going a little faster, but I hope that's okay. In the text, they actually even say, oh, give a formula. So the text gives a formula of how to write this down. I don't want you to use the formula. Okay, so please do not use the formula, because I want you to show that you know how you get to the recursion relation. Okay, they write out, and it's a lot of formulas, actually. It's just not one formula, it's just a lot of formulas, and that I don't want to do. Okay. And by the way, so what I will ask, sorry, I should have said this here, but I will make it explicit on the quiz. Find up to degree 5. So A0 up to A5, that's what I mean. Okay, so well, we can expand this as n squared minus n plus 1 minus 2, so minus 1. Now we do have to do a shift here. So and one of the things I want to see is that you know how to do this shift. So this is n goes to n plus 2. And that means summation n plus 2 times n plus 1 times an plus 2. And now we get the right power, x to the n plus summation an x to the n. And this was n squared minus n minus 1. And this is equal to 0. Now we have all powers of x to the n. So the coefficient of each of these powers has to be 0. And so we get the equation that we want. And we always solve for the highest degree, right? So you an plus 2 is equal to minus n squared minus n minus 1 divided by n plus 2 over n plus 1. I hope it's okay I did this this I skipped a step here, but if you don't see this, how do I skip the step, please stop the video and write down the step in between. Okay, figure it out, bring it to the other side, then divide. Okay, right, so this is our recurrence relation. As I said, this is one thing I want you to do. I'll make it explicit. I didn't write it down here, but it was just a review. But on the quiz I will say, show me the equivalence relation. Now once you have that, now you can start calculating all the values, right? So I'll make a little table here. We have A0, A1, A2, A3, A4, and A5. Okay, A0 was 10 and yeah, right, so this is A0 and this is A1. That's another thing, of course, that you need to know from this. That is why we have at the center, if we take 0 to be the center, then y0 is the first term and y1 is the second coefficient, the first coefficient and the second coefficient, yes. So 10 and 40. Now A2, how do you get A2? Well, that is from n equals 0. There's no need to go for even and then odd. That's what they do in the textbook because they're trying to find a formula. We don't want a formula. We just want A2, A3, A4, A5. Just we, in other words, in this recursion relation, we plug in n equals 0 to get A2, and then 1, 2, and 3. And then we have everything we want. So if I plug in n equals 0, that gives me A2 is equal to minus A0, 0, 0 that, times minus 1 over 2 times 1. So that's minus minus is plus. So we get n is 0 is 10. So 10 divided by 2, that is 5. Okay. A3 we get from plugging in n equals 1. That is minus A1. If I plug in, what am I plugging in? N equals 1. Right, so write that down that you forget. Otherwise, you start plugging in 3. 1 minus 1 minus 1, so that is negative 1. And in the bottom, I get 3 times 2. So minus 1 was 40. Minus minus, yeah, so minus minus. Wait, did I do this right? Plug in n equals 1, right? 1 minus 1 minus 1, okay. In the bottom, I get 3 times 2, okay. A1 is 40. So I get A1 is 40 over 6. That is 20 over 3. And then A4, that is by plugging in n equals 2. I think I took the wrong value here. I think I wanted to have this to be 60. Sorry, let me make it 60 so that I don't want to have any. So it's 60 divided by that. I copied it wrong from my notes. So that is 10. Okay, so A4 is gets from n equals 2. So if I plug n equals 2, we get minus A2. And then we get 2, that is 2 squared, 4 minus 2 minus 1, divided by... Oh, I see where I made a mistake. I copied, that's why my numbers are not the right one. It is a plus 2 here. Why do I make a minus 2 there? So I guess this was 40, sorry. It doesn't matter really, but let me get it, stick to the 40 that I had here. But I made a mistake because I copied it wrong. There's a plus here. So there's a plus here. So there's n squared minus n plus 3. And oh, this is an n. I don't know what was I doing here. Look, sometimes if you go too fast, you make mistakes, right? So I apologize. So a lot of things I made mistakes here. We had n minus 1. That is this one. We had n, that is this one, and we had 2, that is this one. I'm sorry, that's where I went too quick. So this becomes n squared minus n plus 2. Yeah, and so that's n squared plus 2. So this thing was wrong. This is n squared plus 2 here. So also the top here is wrong. So these numbers are, let me get rid of these numbers here. I think I made a mistake here. No, I don't think, yeah, no, I think. No problem, yeah. No, I mean, let's do it over again. So this, as I said, is n plus 2. Squared plus 2. Okay, so now plug in, what do we do? N equals 0, that is a2. That is minus 2 times a0 over 2 times 1. So that is just minus a0. And that is minus 10. Yeah, okay. So a3, that is we get for n equals 1. So then we get minus a1, and then we get a plug in 1, so I get a 3 there, and in the bottom we get a 3 times 2, so the 3's cancel, I get minus a1 divided by 2, that is, this was 40, right? I'll go back to what I originally said, minus 20, n equals 2, a4, so now we plug in n equals 2, right? So minus a2, then we get 6, 4 plus 2, right? On top, and in the bottom I get 4 times 3. The 6 with the 4 times 3 cancels, the 2 left. And so minus e2, that is minus 10, so plus 10 divided by 2, I get 5. A3, oh, A3 I didn't write it up here, A4 is 5. And finally, if n is 3, I get A5. So I plug in 3 again, so minus A3, I get 9 plus 2, that is 11. And in the bottom I get 5 times 4, and minus a3, that was minus 20, minus to 20, so 20 times 11 divided by 5 times 4, okay, that is 11. I cancel out. Okay, so that was one of them. And then the other one I want to do is this one here, 2x squared plus 4x plus 3 y double prime plus 3x plus 1 y prime minus 3y equals 0, and the initial conditions are y in negative 1 is 8 and y prime in negative 1 is 5. So here, by virtue of the fact that we have initial conditions at negative 1, this means we should center it at negative 1. So we're looking for something of the form x plus 1 to the n. The power series in x plus 1 to the n. But if that's what we're going to do, then we have to write all these polynomials that occur here as coefficients also in powers of x plus 1. So I'm going to, and that the trick is of course to write x itself as a polynomial in x plus 1, this very obvious way, and then plug in. So we get 2 times x plus 1 minus 1 squared plus 4 times x plus 1 minus 1 plus 3. So I know it's weird that you don't expand the x plus 1s here and simplify, but the whole purpose is to get everything into this x plus 1. So this x plus 1 is now a unit that cannot be destroyed for our purposes. So we have to do the double product formula here, that is x plus 1 squared minus 2 times x plus 1 plus 1. And here we expand is 4 times x plus 1 minus 4 plus 3. So we get 2 times x plus 1 squared minus 4 times x plus 1 plus 2 plus 2. There's a plus 2 minus 4 plus 3, so that's altogether plus 1. Plus 4x plus 1. Sorry, I should write that one. And then we have 2 times 1, that's 2, plus 3 minus 4, so plus 1. And this cancels out. This is just because we are in the easy case. In the cases that the next section we talked about, when we talked about 7.3, and so there we would not have this kind of simplification. But in principle, there's no reason for the simplification. It's just they decided in the textbook to devote a special section to it, and I kept it that way. Okay, so this means what? That we're gonna have to plug in. We have this, and then we plug in the double derivative. Now, I'm going to write down the double derivative already, because we have done it so many times. I guess it should be clear that that's what it is, right? But don't forget it's powers of x plus 1. Then plus 3 times x plus 1 summation n a n x to the power x plus 1 to the power n minus 1 minus 3 times summation a n x plus 1 to the power n. Now, in the expansion, the first one here, let's do this first. That is the one that we have to do a shifting, because this will have the wrong, is arranged in the wrong powers, but the other ones are all fine. So again, we're going to factor out an a n x to the n, and now be careful, and that's to myself that I'm talking. This times that, that's 2n n minus 1. Then we have this 3 here and the n, all these things I forgot last time, and then minus 3 here. So minus 3, that's it, equals 0. Yeah, well, right. So we have to do the shift here. So n goes to n plus 2. We only have shifts of degree 2 here because we are order 2 the differential equation. But this in principle can work for higher orders as well. So we get an n plus 2, n plus 1, a n plus 2, and now the power is the right one, plus this factor, plus the other sum, so I'll write it up. So now we have everything in powers of x plus 1. Oh, I say that we have to be careful, I have to write it in powers of x plus 1 and write powers of x here. So now we look at each of these coefficients. So in other words, this together plus this is now 0 with the an here. All right, this is now, okay, if you want to write it, I'll write it one more time. So what is the general coefficient here of x plus 1 to the n? Well, we have this n plus 2 times n plus 1 times a n plus 2, and plus, and then this one we can perhaps already 2n squared minus 2n plus 3n minus 3. So that is 2n squared plus n minus 3 times a n. Okay? And this is equal to 0. This means that these guys has to be equal to 0. And we solve always for the highest one, so we bring that to one side to get n plus 2, n plus 1, a n plus 2 is equal to minus 2n squared plus n minus 3 a n. And so we find our recursion relation, a n plus 2 is equal to a minus 2n squared plus n minus 3 a n divided by n plus 2 n plus 1. So let me check here that I got this. Okay, so this is the recursion relation. And now we can write down the values. So a0, a1, a2, a3, a4, and a5. So a0, what I say was 8. Because, right, this is a0, right, and this is a1. So 8 and 5. 8 and 5. So what do we do now? We need a2, and that is from this recursion relation by plugging n equals 0. Don't plug in n equals 2, because we plug in we want this side to be a2. We don't want a2 here. Okay, if I plug in n equals 2, I get a2 here and a4 here. How am I going to calculate a2 if I don't know a4? Right? And recursion relation is the one thing you have to do is you have to solve it in the right order. You cannot solve the third one before you solve the second one. Okay, so we have to do a2, and for that we need n equals 0 in here. Okay, so this is a2 is equal to minus, what on top we get minus 3a0, and in the bottom we get 2 times 1. And the 0 was 8, so this is minus is 24 over 2, that is 12. And then we do the same thing to find a3, but now n is 1. So minus, we get 2 plus 1 minus 3, a1 over 3 times 2. But 2 plus 1 minus 3 is 0, so this is 0 no matter what a1 is. Okay, so, but okay, n equals 2. Now we're going to get a4, and a4 will be minus a2, right? So this now is 2, and then we plug 2 in here, and we get 8 plus 2 minus 3, and in the bottom I get 4 times 3. So that is 7 over 12, so it's minus 7a2 over 12, and A2 was 12. Oh, so this is minus 7. Oh, that was A4, sorry, minus 7. What was A3? Oh, A3 was 0, right. A3 was 0. So, can you guess what A5 is? So, one of the special things about this particular type of differential equations that are studied only in 7.2, don't confuse this with what happens in 7.3. But in 7.2, the form of the differential equation always has the phenomena is that to find the value of a particular element in the sequence, the AIs, you go 2 back, right? From A2 you go to A0, from A3 you go A1, from A4 you go A2. You jump by steps of 2. So it's not the previous one, but the one before that, the penultimate one that governs the thing. And therefore, we have seen that if you work this out slightly different in a different order, you can see that the even ones are all determined by A0, and it doesn't matter what A1 is, so the A0, A2, A4 all depend on the choice of A0, but A1 can change, and as long as A0 doesn't change, the initial condition A0 doesn't change, they will always have the same value. And the same is true for the odd ones. Because of this jump of 2 between the two indices. Therefore, this means that the odd ones will all depend on the A5 will depend on A3, but A3 is 0, and A7 will depend on A5, which depends on A3, which is 0, and which therefore A5 is 0, therefore A7 is 0. So without calculating, we know that A5, A7, A9, and all these are already 0. Now, of course, you can plug it in and you'll see it. Why? Well, because of this 0 here, of course, right? I mean, if you didn't see it right away, once you plug it in, you realize, oh yeah, of course, I should have guessed that. Okay, so this is 0. Okay, but that doesn't mean that the A6 will not be 0, right? So it's not that this is a polynomial. The solution will be a real power series, because the A6 and A8 and so will not be zeros. Okay, so that's a bit of all kind of things that can happen in this, because this is the easier part of the solution. But so I'll stress again, although the book has brought all these formulas and all this fancy discussion, I don't want you to do that. I want you to do exactly what I'm doing. In particular, I want you to show me how you get to the recursion relation. So I need a recursion relation, and I need to see that you do the right shifting here, that you do this step correctly. It's not that much. In 7.3, the next quiz, there will be a little bit more writing and more work. But here, so this is the preparation for that quiz if you want. That's why I want you to do it this way. Because the formula that they have in the book, why don't I teach you this? Because for 7.3, for what we have seen in 7.3, it doesn't apply. So you learned the formula for something that was not it was not helpful anyway. I think one should only work with formulas that work all the time. If a formula only works in special cases, then okay, then you could as well just do the special case. All right.